Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Ajmal Danish bin Muhammad Jamri. My matric class number is CE210217. Now I will present about the leg 4, the high voltage. Okay, the task 1. The title is analysis of electric field between electrode. Okay, as we can see, this is the electrode. So before that, I will show you the example how to draw the gap for 7.5 cm by using the apps FEMM software. Let's go design the problem. Okay, after design the problems, okay, we need to setting for this is the open boundary, and then for this section we need to put the element for air element, and then for this is the high voltage element, and then for this section this is the ground section. Okay, before that we need to go the properties, and then we need to setting the material of air, what the value of air. So go to modified property, and then we need to put the value of air is 1 relative, and then charge density is 0. Okay, and then click OK. After that we go to the boundary, set the value for coefficient open boundary is 1.180, and then click OK. After that, lastly we need to go to conductor. Okay, and then we need to set the HV and ground element. For the HV, for this HV high voltage, the voltage for 7.5 cm gap, this is the 196 kV, and then the ground, the value is the voltage is 0, and then click OK. Okay, firstly set this open boundary. This element is air. Don't forget to set as default block label. And then this is the high voltage. And then we need to run. We need run this simulation. Okay, after that, we can see the value for we can see the electric field intensity for in the electrode. Okay, now next we need to see what the value for electric field intensity for in the 7.5 cm gap. Let's go choose the field intensity. And then we can see the lower bound is 7.27 and the upper bound is 27585. Okay, next we need to see where the highest electric field intensity. Okay, let's go. We need to see the value of electric field intensity in the graph, and then choose the magnetic of field intensity. Okay, lastly this is the graph for 7.5 cm gap for electric field intensity. Okay, that's all from me. Thank you.
Assalamualaikum. Okay. So my name is Alif Aiman bin Azahari, and my matrix number is DE2100701. So I'm gonna continue on task number 2, which is analysis of force of a gap CI core, which is this is the figure 2.2 CI core electromagnet. As you can see, this is all the measurement for the CI core that we're gonna do it next. So at first of all, I want to show you how actually it's look on the lab sheet. As we go to the FEMM, so this is the CI core that I already done, which is every every coordinate has been plotted based on the coordinate based on the lab sheet, which is, for example, for this one, each gap from this point to this point is about 0.1. As we can see from here, it is very close. It is 0.1 cm. So if we take a look at this, all this put inside is air. As we can see at the top right corner, there's air in the circle. Yeah, this is it. That means the surrounding is full with air, and the CI core, which is we put in the properties material, which is M15. How do we get the M15? Is from here, from the material library. Okay, we go to the M50 here. M50 we can get from around here. Okay, for example, this one, this is the M50. Okay, for the 10 AWG, we can get from the copper AWG magnet wire. Okay, as we just press the file, and then we can see the 10 AWG. Okay, and how do we use the AWG? Is we only drag them from here, move to right. Okay, that's how it works. Okay, and then I forgot on how to make the plot from all of this. Okay, for example, if we take a right click or left click, then we just a dot. Okay, but the coordinates, it won't be different. I'm sorry, the coordinate will be different because we are not set the coordinates. I guess my friend Ajmal already explained them earlier. So I'm gonna take a just flashback. Just press the tab. Okay, now we can set the coordinates. So how do we set the coordinates? I believe the person who watched the video already know based on Ajmal explaining, but I'm just gonna take a flashback. So for example, we want to do the I core. Okay, so as we can see here, the I core is only gap 1 cm. Okay, only 1 cm. So what we're gonna do? So the X is, we try put 9, and the Y core we put 10. Okay, and then we press OK. So this is the coordinates. So the next is, just now we put what we put just now. If we want to take a look back, our dots is just take a right click. Okay, now in red, and then press tabs. Okay, now it shows 9 and 10. Okay, so what we're gonna do is we press tab for another new dots, and we press 10, and the Y chord will be the same, which is another 10. So right now we have another dots. So from dots A to dots B, only 10 cm. Sorry, only 10 cm. Make it back. Okay, now how do we connect the dots? As you can see here, at the left top corner, they have the line. So what we are gonna do is we click at the line dots A, and dot B, and then the line will happen. So that's how it's work. Okay. Okay, now we're gonna try to simulate the circuit. Not the circuit, I mean this DCI core. Okay. What we're gonna need to do is we press this one. Sorry. Okay. As we can see, the magnetic field this is the magnetic field which goes around the surrounding. It happened because of air. Okay, we go to the next step, which is we want to see the flux density. Okay, we press this box, and we press OK, and the color will show up. Okay, sorry, I'll try to zoom in. Okay, so if you want to see the exact want to see this one, sorry, okay, if you want to see the exerted force, okay, what we're gonna do is, firstly, we're gonna see the exerted force around at the I core, which is this one. So we left click on this I core, and then we press the integrate. So we're gonna search for is this one, the force via weight stress tensor, and then we press OK. So this is our answer, which is the X component, which is negative 799.66.8, and the Y component is negative 0.06. Yeah, this is the answer, and this is the task for number 2, which is this one, the analyze of force of a gap CI core. That's all from me.
Hi, my name is Ahmad Fikri bin Muhammad Unaski, and my number metric is AE200004. Alright. Today I would like to explain about an extensive discussion on the results. These experiments produce graph of voltage and potential electric field for electrodes of various shapes. In example, spheres. This experiment is highly dependent on the applied voltage and the gap distance. According to task 1, a pair of spheres with one grounded terminal must be made using FEMM, and there is an asymmetry problem to draw the shape symmetrically. Next, half of the shape of pair of spheres must be drawn. Lab instruction sheets are used to record diameters, radius, and other data required for simulation results. When a voltage is placed between the electrodes, there is a difference in ability to produce an electric field. The electric field determines the strength of the electric field experienced by charged particles. The electric field flows from the positive velocity side, high voltage, while the electrode flows toward the negative, which is low voltage side. Thus, the magnitude and distribution of the electric field between electrodes is influenced by the characteristics such as geometry, diameter and radius, gap distance, and applied voltage, which is kV. The shape of placements of the electrodes affect the distribution of the electric field, and various configuration allow them to produce different electric field patterns. The electrodes were designed with an asymmetric form and a gap spacing ranging from 1 cm to 17.5 cm between high and low voltage conductors to maximize the electric field simultaneously. The electric field intensity, which is Emax, is expected to decrease as the gap distance increase. The connection is based on the fundamental electrostatic principle, which is that the intensity of the electric field decreases as one moves away from the source charge. In the conclusion, from this task 1, as the electrodes move further away, the electric field between them will decrease correspondingly, resulting in a decrease in Emax. Okay, we go to the discussion on field uniformity. In experimental studies, electrode shapes and spheres have shown great depth in electric field distribution. However, the distance between these electrodes is one of the main parameters that determine the exact uniformity of the field. In fact, as mentioned, the width between the electrode directly affects the amplitude of the electric field and forms a region where the strength of the field gradually decrease. On the other hand, reducing the distance between electrodes explains the ability to improve the uniformity, but the challenge related to the shape and position of the anode and cathode may confuse the practical implementation. In particular, the air permeability characterized by the permeability coefficient of 1 did not change by increasing the electrode distance in this study. We go to the conclusion. In this design project utilizing the finite element method, which is FEMM, for magnetics, we have successfully employed advanced and computational techniques to analyze the optimized magnetic components and the systems. Through the systematic methodology outline, we address key aspects including problem definition, geometry modeling, finite element meshing, boundary condition, solver setup, analysis, optimization, validation, documentation, and iterative refinement. Overall, this project demonstrates the efficiency of employing the definite element method in the design and analysis of magnetic systems, paving the way for innovative solutions in various fields such as power electronics, electric machines, transformers, and magnetic sensors. Through continued application and refinement of this methodology, we can further advance the state of the art in magnetic design, leading to improved efficiency, performance, and reliability in engineering application. Thank you. That's all from me.
Next is discussion. First is gap dimension and core force. First, larger gap in the magnetic core lead to the stronger forces experienced by the core. This happens because bigger gaps disrupt the magnetic path, making it harder for magnetism to flow through, resulting in increased force. It is essential to carefully choose gap dimension during transformer design to optimize performance and prevent mechanical stresses on the core. 2. Core materials and core forces. Different core material affect the force experienced by the core differently. The ferromagnetic material like iron have higher magnetic permeability, which concentrate magnetic flux and lower the force on the core. Choosing the right core material is crucial for the achieving desired performance and reducing mechanical stresses in the transformer. 3. Operating condition and core force. Changes in operating condition, such as voltage and frequency, can impact the forces experienced by the core. Higher voltage and frequency intensively magnetic flux leading to the increased forces on the core. It's important to consider operating condition during transformer design and ensure robust insulation and mechanical support system to handle varying forces. Lastly, conclusion. This project delved into magnetic circuit analysis, focusing on how gap affect transformer performance. We review previous research on gap CI core transformer to set the stage. Our goal was to create a model to analyze magnetic flux and force in this transformer, considering gap size, material, and operating condition. Using advanced simulation software, we scrutinize transformer behavior. Our simulation reveal how gap size, material, and the condition affect core force. We validate our model through experiment confirming its accuracy. Overall, our study enhanced understanding of gap CI core transformer, offering practical design insight and paving the way for technological advancements to improve efficiency and reliability.